this is Lab 5, Faraday's Law. One of the main goals of this lab was to explore the interactions between a bar magnet and induced currents in tinfoil that are created due to Faraday's Law. Some of the major physics principles in this lab were Faraday's Law, magnetic force, and Newton's second and third laws. Through the application of the procedures in this lab, we were able to observe the change in speed when we dropped a magnet through a tinfoil tube and then create a computational model to illustrate this interaction with the same time it took for the magnet to fall through the tube. So this is my setup I repeated 5 times where I dropped a bar magnet through a tube of tinfoil roughly 1 centimeter thick. As we're able to see in this video, the magnet appears to fall slower through the tube than it would without it. Over the course of the 5 observations, the magnet appeared to fall through a little less than a second, or about 0.9 seconds. We'll use this value to compare it to our computational model. We use GlowScript to create our computational model. We have our physical constants, and then we were able to create our tube and our bar magnet using observed values such as the length and width of the tube. And then we created the bar magnet using our value of mu we calculated in lab 3, which was 2.696. And we also have our 2 functions here, which the first one calculates the magnetic field created by the magnet. The third one calculates the magnetic flux from the magnet. We then were given a simulation loop where we had to do a few edits. First, we created what the gravitational force would be on the magnet, which is just negative mass times the gravity constant 9.8 in the y direction. And then we have another loop that calculates every simulated ring in the tube and finds the change in flux and then uses that change in flux to find the current of each ring. We then use all of the functions above to calculate a magnetic field at a typical point on the ring. We use this and our calculated sine theta to figure out the magnetic force from the ring onto the magnet. This would be in the y direction going up. We then calculate the net force, which is just the addition of this magnetic force and the gravitational force. We then use this using Newton's laws that the velocity of the bar is just the force divided by its mass times change in time, which is the acceleration. And then the position can be calculated using this velocity times the change in time. When we run our program, we're able to see the magnet fall through the tube. It took roughly 1.04 seconds for the magnet to fall all the way through the tube, as we can see here. And the rings that were created as it fell through were the different direction of currents that are created by the magnet. So as the magnet's falling down, the change of magnetic field is going down, but the negative would be going up. So this creates the red color that is a counterclockwise current. And the blue current is when the negative change is going down, so it goes clockwise. Flipping the magnet wouldn't really change much of our results, as there would still be a force trying to push the magnet up instead of down. So we can see our velocity versus time graph here. As the magnet is initially dropped into the tube, it accelerates rapidly, which is illustrated by the sharp slope. But as it reaches fully into the tube, the magnetic force from the ring begins pushing up on the magnet, causing it to slow down as the velocity goes up a little bit more. And then it approaches a rough constant throughout the tube until it reaches the end where there isn't much magnetic force pushing it up, and the acceleration happens again, causing the magnet to fall off the tube. So we were posed a few questions. What if the resistivity of the conductor were reduced as close as possible to 0? How would the dynamics of the falling magnet change? If the resistivity were reduced to as close as 0 as possible, the magnet would not fall into the tube, but instead it would fly up in the air as the induced current in the foil would be extremely large, causing the magnetic force to be much higher than the gravitational force. What if holes or slots were cut into the tube? How would this affect the ring currents in your model? If holes were cut into the tube, there would not be any current created in the rings because the current would not be allowed to continually flow. I was able to create an accurate computational model of the magnet falling through the tinfoil that was fairly close to my observed value of time the magnet took to fall through the tinfoil tube, which was about 1 second. Additionally, the computational model in this lab allowed me to fully understand how Faraday's law works and how induced currents create a magnetic force of the magnet acting on them. Thank you.